Hey guys, welcome to another episode of Black Guy Does Physics, where apparently we podcasting. Well, if you have any issues with like physics problem, math problems, need some help, hey, holler at me. Leave a message, comment somewhere down there, and smash the button. Or as they say, smash! Okay, with that being said, let's get it cracking. Today we're looking at AP Mechanics. We're back to mechanics again because my boy Spicy said, let's go. So I'm getting it done. This is 2016, number 3. Mechanics, mechanics, mechanics. All right, let's see what's happening here. So first things first, once again, you see a problem, you want to figure out what's popping with the problem by looking at the diagram itself. Get the concepts in your mind of what's happening. So I see spring, right? So if I see a spring, I know that there's a couple of things associated with a spring. It's either energy, forces, or SHM, which is simple harmonic motion. So one of those things. I see this thing that is rotating. So if I see something rotating, it's usually torque, which is I alpha and also equals to RF or R cross F. And forces usually involved, if there's some forces somewhere in there, probably not, or kinematics, if they give you some information. So once again, you spend like 10 seconds on that, making that association in your head. If you want to write it down, you write it down. Why? Because you could go back later on to see what you should be talking about. So let's see. So there's something attached, spinning around. A uniform rod, uniform, of length D has one fixed end to an external central axis of horizontal frictionless. So it's horizontal. So that means we're looking down on the top view. And the radius is 2D, so R is 2D. Fixed at the other end of the rod is an ideal spring. Ideal spring means that F is equals to minus kx. We're good to go. And it would do simple harmonic motion. Negligible mass to which the block is attached. The block is set to in a frictionless groove, so no friction acting on this thing, so that it can only move in a radial platform as shown in the figure. The equilibrium length of the spring is D over 2. Okay, so D over 2. So the rod is D and the thing is D over 2. Yeah, the rod length. Oh, okay. Okay, so in figure 1, it's just chilling. Below the table show the mass and blocks of the mass and rotational inertias. So if they're showing rotational inertias, that simply either means that you're going to be looking at torque or something. Maybe. I don't know. So they're giving you the mass and the rotational inertia. Oh, crap. They didn't give you the one for the block. Okay. All right. As the motor begins to slowly rotate, no, this is a long-ass question, slowly rotate the platform counterclockwise, as viewed from above, I said it was from above, until it reaches a constant angular velocity. So if it's a constant angular speed, then that means that the torque net is equal to 0. And the angular acceleration is 0. So this might not have anything to do with torque. Under these conditions, the spring attached by an additional is stretched, I can't read, by an additional length D over 2 as shown in the figure. All right, sweet, no problem. Answer the following questions for the platform rotating at a constant angular speed. Express all algebraic terms in terms of blah, 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 and the physical constants as appropriate. Derive an expression for the spring constant of the spring. Ew. So what usually happens here is that students usually get bugged out, man, because they say spring constants and they had no idea of what they're supposed to be doing here. Absolutely none. Well, once again, then all you do is go back to your things here. Just go back there. So they're asking you for spring constant. There's only 2 places that you see spring constant. It's either energy, where the spring potential energy is 1/2 kx squared, or you have the force, where it's F is equals to kx. So there's no way that you could use what should I say? There is no way that you could use, what's that thing? Energy in here, due to the fact that you don't have, hold on, you don't have anything to do with energy. So therefore, you're going to see that you'd have to use the spring force. But then again, I think I missed something over here. Oh, my bad, son. They said it was going in a circular path. And once you see circle with forces, that's centripetal force. Oh, snap. That's why you gotta read. They done got me. It's circle. So it would be the spring force would be the centripetal force because this thing is turning around. The only thing you could use to find K is the spring force. But at the same point in time, there's nothing else that you could associate K with to find. So you have to notice that whole low-key them boys said circular platform and they gave you the angular speed, son. So that means that you'd have to set this up as the spring force, which is kx. We're just looking at the magnitude, is equals to mv squared over r. However, broski, because this is moving in a circle, you have to remember that for kinematics, Jesus Christ, there's a lot of memory here. You'd have to remember that you could rewrite v as r omega. I should have written that down. That's one of the things, and a is equals to r alpha. But we already said that the acceleration is going to be 0, the angular acceleration is going to be 0, so we ain't even tripping on that. So v is equals to r omega. So if you punch that in, you're going to have kx is equal to m r omega, and that would be squared over r. So you'd have kx is equals to m r omega squared. Dope. Therefore, k should be equals to, what the hell is x? X is how much the spring has been stretched. So x, remember, k is the spring constant, x is the distance this thing has been stretched. Therefore, you have to rewrite x as d over 2, which I should do here. K d over 2. Remember, the junk got stretched from d over, this was the equilibrium length, and then it got stretched another d over 2. So that would be d over 2. So let me erase this junk, put d over 2. So now I do a little bit of math magic. So that becomes 2r omega squared over d. I think that's correct. Hopefully that's correct. Yep. All right. Keep it moving. I think that's correct. Did I miss something? Why my black spidey senses are tingling like I think I missed something. If not, you could always make a comment in the bottom. Let me know if I missed something. Remember, we're doing this one shot, man. And no takes backsies. All right, let's keep it moving. Determine an expression for the rotational inertia of the block around the axis of platform. Oh, the block, right? That's easy. So the block is, you're going to treat the block as a point mass. See that thing? So for a point mass, what is a point mass? I'll say this slowly. For a point mass, it's anything that is doing this type of junk where it's rotating, going around, but the axis of rotation is not on the object. So you see, the block is right here, right? But the axis of rotation is here. But the block is going around the axis of rotation, and it's attached to this setup. But the block itself is here. So you're going to treat this as a point mass. And for a point mass, then it becomes why is it a point mass? Because the axis of rotation isn't on the object itself, son. It's not on the object itself. Therefore, if it's not on the object itself, you simply just treat it as a point mass. Oh, I'm so silly. R, what's R? R is the distance. That just popped in my head. I told you my black spidey senses was tingling. I'll go back to here. R, I was like, yo, this looks weird. R, because you can't leave it. It has to be in terms of M, D, and omega. My apologies. R is D, bruh. Because look, it's gonna be R. R is the radius. Right? So you could see that the radius would be, what, 2D? Yeah, 2D. R is the radius, 2D. That's D over 2, that's D over 2. That means that's 2D. Yeah, my bad. So now I have to do this, finish this up before I go back there. 2D omega squared over D. Yeah, so D cancels D, so you have K is equals to 4 M omega squared. My bad, bro. I forgot. See? I didn't underline. I said blah, blah, blah. Yeah, that's a mistake. Don't do that. Anyway, back to this rotational inertia for the block. So I should just be equals to mr squared. And if it's mr squared, then m is just m, and r is, we just said that r was 2d. Do that. What? 4md squared. I'll take that. I'll take that L, not L, W's. We don't want no L's over here. Strictly W's. Oh, that was easy. Determine an expression for the rotational inertia of the entire system and the platform. Oh, they did give us this crap. So this is what? 4md squared. So all you have to do now is just add them junks up. Because remember, moment of inertia is like, or the rotational inertia, it's like the rotational mass. So because mass is a scalar quantity, the rotational inertia would have to be a scalar quantity. That simply means that you could just add those junks up together. So the total, I total, would just be equals to I for the block plus I for the, what's this junk called? The rod, and I for the platform. Right? And then the block is what? 4md squared. And the rod is 3mrd squared over r. 3mr d squared over r plus, what is it? Plus, what is it? mp r squared over 2. And then you're going to substitute in there, right? So you're going to substitute, what is this? Is it over r or over 3? No, it's over 3. So it's 3mr d squared over 3 plus, what's big R? Big R would be the total thing of that, so it would be 2d. So that would be 2m2d squared over 2. And simplify that, man. When you simplify that, I think it becomes 15. Ooh, I'm writing in this one. I'm running out of space. This is a horrible podcast, but you get the gist. The sauce is good. 15md squared. That's what you get. You get a point. Add them up. And R is just, the big R is just the thing of the platform. The radius of the platform, which would be 2d. Okay? Determine an expression for the angular momentum of the entire system. Angular momentum, what does that equal? L is equals to I omega. I think that's what it's equal to. Yep. So, sweet. 15md squared omega. Clutch, done. No trick there. Oh, sweet. Thank you, sweet baby Jesus. Baby Jesus. While the system continues to rotate, a small mechanism is in the pivot, moves the rod slowly until the center of the rod is positioned on the axis. Okay, so they chop that into a half as a rod. The same constant angular speed is maintained by the motor driving the platform. Derive an expression for the distance the spring is stretched when the rod reaches the position. So they want the distance x of the stretch of the spring. So right now my brain is drawing a blank. I'm like, what the hell are they talking about, bruh? So what do? I just go back and go, okay, I'm looking for x. Where do I see x, which is spring stretch? There's only two places. U is equals to half kx squared, and F is equals to minus kx. All right, I still can't do energy, so this must be F. And this junk's still moving in a circle, yeah? I think so. So let's try the same thing we did before. Like, the spring force has to still be equal to the centripetal force. Yeah, bruh. And then we already know that this is mv squared over r, and we saw that that was mr omega squared. And my spring force is still kx. But unlike before, now I know what k is, remember? I just solved for k. Where's k? The hell are you, k? 4m omega squared. Yeah, clutch. 4m omega squared x equals to m r omega squared. I think m's cancel. I think omega's cancel. And I think x is equals to r over 4. Am I correct? Did I do that right? R. I keep doing this R thing, dude. See, I keep making this mistake. What is R now? R would be the distance, because you can't write it in terms of R. Come on, get your head together, man. I'm being a straight moo right now. R would be from here to here. So you could see the traps. I'm so glad I'm doing this like one shot. You see? That's why I always do my videos one shot, so you could see the mistakes as we're going on. You can't write it in terms of R. R is not there. You have to remember that. So what exactly is R? This would be a half a D, right? And this would be a half a D, and that would be X, because that now is the new stretch distance of this thing. So you have to write it in terms of that. So if that's the case, what we have is what? 4m, what is it? M omega squared x is equals to m. What is R? R would be half a D and half a D. That's D plus X. So I think omega squared cancels omega squared. M cancels M. So we have X, 4X is equals to D plus X. So X should be equal to, I bring over that X, that would give me 3. It would be D over 3. X would be equals to D over 3. Oh, don't get trapped like that, kids. Them boys setting traps everywhere. For parts E, F, G, assume what? There's a G? Did I not copy the G? Oh, no. Oh, yeah, I did. Assume the center of the rod is still moving towards the axis of the platform. Is the angular momentum of the entire system increasing, decreasing, or staying the same? That's a good question. What is the angular momentum? The angular momentum would be L is equals to I omega. They did say, wow, you'd have to remember that they did say that the speed is keeping constant. So you got to underline things and remember. The angular speed is constant. So if this is constant, right? And this, what is happening to this? If this is staying constant and this is constant, is the I staying constant? No, the I cannot be staying constant. Why is this so? Because the radius of the whole thing is shifting. The axis of rotation on the system is shifting. Because you could see at one point it was at the end, now it's in the middle of the rod. So the I must have shifted, right? If you move the whole system closer to the axis of rotation, the moment of inertia is going to drop down. That is how inertia works. The closer the mass is to the axis of rotation, the lower the moment of inertia is. You could do that anywhere. You could try that. I should make a video where I'm actually doing a little lab on this to explain that to you. So the answer should be decreasing. Why? Because of what I just said. By moving the rod inwards, the moment of the inertia of the object is dropping. F. In order to keep the system rotating at a constant angular speed, the motor is doing positive work, negative work, or no work. So, this is a tricky question too. Let's talk about what positive work and negative work does. If you're doing positive work, the whole system would speed up. If you're doing negative work, the system would slow down. Cool. But the system is staying at the same speed, but you're reducing the angular momentum. So if you're reducing the angular momentum of something and it's keeping the same speed, that simply means that, no, if you reduce the angular momentum of something and it's spinning, then the angular speed should increase. The fact that the angular speed isn't increasing, that means that you have to apply something to make sure that this thing is going slower, which means that this thing should be doing negative work. Hopefully that made sense. You could replay that statement again because I don't want to make the video too long. On the block, draw a single vector, represent the direction of the acceleration of the block draw on a vector so that it starts there. Which way? So most students would be like, yo, it should be straight because the centripetal force is always to the inwards, which is true, but you have to remember that you have a bunch of forces act together to give you that thing. You see what I'm saying? But this is the acceleration of the thing. That's not the centripetal force. The centripetal force is just the radial force. But remember, the actual acceleration of the object is in 2 days. You have a vertical component. So I'm going to put this in blue. So you'd have a vertical component, or a radial component, I should say, and you'd have some tangential component, right? But you could see in this particle case, if it's slowing down, or if there's some torque that is acting on it to slow it down, then it would be in this way, or trying to slow it down. Therefore, it's this way. So when you add these two junks together, then the resultant would be somewhere like this. So that's your actual acceleration, right? So that wasn't too bad, I don't think. But as you can see, I was doing the stuff, man, and it will trick you. So I would advise you, as you're going through these questions, kind of slow it down at times. Don't try and rush it like me, and check to make sure that you're using your concepts and you're using your equations together, right? If you see anything I made mistakes in here, you could. I'm glad when I make mistakes, because you could see that as I make mistakes, I try to correct myself. This isn't one of them fancy ass videos where it's just, ooh, this is all you. Nah, man. We do real time, real things here, and one thing we do is not be a mumu.